Good morning, friends. In the last class, we understood how to find out in the equation y is equal to a plus bx the values of a and b by using statistical equations. So let's discuss further and understand some more aspects of the how to analyze the results which are uh, there from running the multiple regression. So we have completed all this stuff, and this was the last slide, and this slide spoke about how to find out the values of y is equal to, in case of the equation y is equal to a plus bx, how do you find out the value of b, and how do you find out the value of a, and later once you have found out the values of a and b, you can find out y predict with the help of the given x values. So this was, in the last class we have discussed all the stuff related to y is equal to a plus bx, and now this is the most important part of our discussion. So in the given example, this is the number of marks secured. This was the actual. This was the actual, and this was the predicted by the given equation y is equal to a plus bx. Okay, and this is the residual. This is the residual. How do you get the values of residual? It is nothing but y is equal to, sorry, residual is equal to y minus predicted y. So this column minus this column, individual elements of y should be, from that you deduct individual items of predicted y. That is, y minus predicted y will give you the residual, or this is also called as error. This is also called as error in the model. Error in the model means this amount of variance is not explained. So out of the, it should have predicted 4. It has predicted 3.56. This model has predicted 3.76. It should have predicted 4 because the actual is 4. So the difference is 2.238718. So this much is not explained. So if you want to say that the model is very strong, then the residual should be minimal. This residual should be minimal, and this should be high. Means the prediction should be high, and the error or residual should be low. So for example, uh, here in case of this particular last item, the actual number of marks secured were 11, but the predicted model y is equal to a plus bx has predicted the actual marks as 10.84, and the residual is 0.16. Means almost 99% is been predicted, only 1% is left out. So this is the way we have to interpret the predicted y, and which is also given by the symbol y hat, and this is the residual. The residual should be minimal, or this is also called termed as residual is also termed as error, and the error should be minimal. Error should be minimal. Next one. So the summary of the residual output, and let's explain this one because this is the summary of our results. Let's take one by one. So these were the number of hours studied. These were the marks secured. Okay, this was the actual marks secured. And when we run regression in Excel on this particular data, we got an equation y is equal to a plus bx. Y is equal to a plus bx, and the values of a are 3.388785, number one, and the value of b, that is regression to coefficient of x on y, is 0.3724. So I modified this equation by substituting the values of A and B, and I got y is equal to A 3.3887, so on and so forth, plus 0.3724, which is B coefficient of x on y, and x as usual. So these are the values of x. These are the values of x. These are, sir, I will call you later, sir. Sir, I am in class. I will call you later. So the values of x is there, the values of y. So this guy has worked for 1 hour. This guy has worked for 1 hour, and this guy has secured 4 marks. This guy has worked for 3 hours, and he has secured 5 marks. This guy has worked for 5 hours, and this and because of this situation, he has secured 6 marks. This guy has worked for 7 hours, and he has secured 5 marks, and so on and so forth. So the data is in front of you. Now, how do you find out predicted y? Predicted y is nothing but y is equal to y is equal to 3.38 3.38. Predicted y is equal to, this is the equation for predicted y. Predicted y is equal to, which is symbol as this one, is equal to this equation I have used, 3.38 plus 0.37, which is b, and substitute the value of 1 because x is equal to 1. So you will get predicted y as 3.76. On similar lines, for the second case, that is case number 2, the same equation to find out predicted value of y, 3.38 plus 0.37. This will be same, but x will change because the number of hours he has studied has increased from 1 to 3. So it is 3. So you calculate this and you will get y predicted is 4.5. Similarly, when the number of hours studied is 5 marks, so what is the value of predicted y? Predicted y is 3.38, same 0.372 into 5, because x is in this case is 5. X is 5 in this case. So if you calculate, you will get the answer as 5.25, which is the predicted y. In the fourth case, the value of the value of x is 7. So I substitute 7 over this place, and this in the equation I will get the value of predicted y is 5.99. So similarly for this and this, and now let's on the similar line look up the last two cases. The number of hours is 18, that is x is equal to 18. I substituted 18 in this equation, and I got 10.09 as my predicted y. Similarly, when my x value is 20, sorry, that is the number of hours studied, what is happening to my predicted value of y? So I substituted 20 in this equation, and the predicted value of y is 10.38. So hope you have understood these values. Now we are going to find out the residual or the error in the model, and individual errors of individual observations. So how do you find out error? So this is the actual number of marks secured, and this is the predicted marks. So the difference is the error. So the error is given by the formula residual, or we use the word residual or error. Residual is equal to y minus y predict. Y predict is also called as y hat. Y hat. Please remember this. In most of the books, many authors use y hat as a symbol like this, and y hat. So the predicted value of y is y4 minus this value. In the second case, 5 minus this value. In the third case, 6 minus this value, and so on and so forth. In the last case, 12 minus this value, and in the last case, 11 minus this value. And when I find out the value, yeah, I will get the residuals like this. So this is the residual. Please remember, if you want to have a model which can predict the independent variable, the error should be less, and it should be it should be almost to zero. Means what? This predicted y should be near to y values. then only the model is said to be a very strong model. So this is one of the interpretations of the output which we get by running regression either on SPSS or Excel or any other statistical tool. Okay, next one. Next one is very important one. The next part of our discussion is to find out uh, there is a ANOVA table. The ANOVA, when we run regression, I will show you there is a ANOVA table like this. There is an ANOVA table like this. When you run a regression on a given set of data, on a given set of data, not only you will get an equation y is equal to a plus bx and the model summary. Apart from this, you will get a ANOVA table, and the ANOVA table has a output like this, which is showing you regression, residual, degree of freedom, sum of squares, mean sum of squares, f value, and significance value. So this is, please remember, this is also called as SSE, sum of squares, error, and this is called as SSR or SSM, and this is called as SST. This is called as SST. So today in this particular session, we are going to find out how did we arrive at this value of SSR, sum of squares regression or sum of square model, and this 12.13, which is called as sum of squares error, and we are going to find out this SST, sum of squares total 64.1. So this particular session is devoted to find out the values of these particular items. Let's discuss this one in detail. So to find out SST, SSR, and this is SSE. Okay, SSR and SSE, we have a table in front of us. We have a table in front of us. So here I have taken the individual values of y, the individual values of y. So 4, 5, so you can look here 4, 5, 6, 5, so on and so forth. So here I have taken in the first column the individual values of y, that is the marks secured by the student depending upon the number of marks, number of hours studied. So in the first case, 4 marks, 5 marks, 6 marks, 5 marks, 8 marks, 7 marks, so on and so forth. Now I will find out the average of these observations, this particular marks, and I found that it is 7.3. So hope you understood this. The formula for finding out average is sum of all the observations by number of observations. Sum of all observation 4 plus 5 plus 6 plus 5 plus 8 plus 7 plus 6 plus 9 plus 12 plus 11 is the total sum of all the observations of y, and divide by number of items, number of observations. The number of observations are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 73 is the total. 73 divided by 7.7 by 10, the number of items, you will get average as 7.3. So I have put 7.3 as average against individual items. So this is the actual y, this is the average y. This is the actual y, and this is the average of y. Now in the previous this one, we have found out the predicted value. We have found out the predicted value. This column we have found out by using this equation, and this predicted y is also kept in this particular table in the third column. So predicted y also is found out. Predicted y also is found out. Now the next column. So these are derived. These are derived. This is calculated, and this is also calculated. This is already there. This was already there. This is to be calculated. This is to be calculated. Already we have calculated this. Now let's talk about the fourth column, y minus, this is y minus y average. Y minus y average. This is 4 minus 7.3 is equal to minus 3.3. 5 minus 7.3. 5 minus 7.3 is equal to minus 2.3. 6 minus 7.3, and so on and so forth. Okay, so this column is y minus y average. Y minus y average. So please remember, this is first column, this is second column, and third column. What I did, 1 minus 2 column. So I get y minus y average. Now y y minus y average. Now next is this one. Next one is this one. What is this one? The square of y minus y average whole square. The square of y minus y average, or y minus y average whole square. Y minus y average whole square. That is 3.3 minus 3.3 into minus 3.3, or minus 3.3 whole square. Whole square. So minus 3.3 into minus 3.3 is equal to 10.89. Square of this one is 5.29. Square of 1.3. Square of, see, symbol doesn't affect, because minus into minus is plus, or plus into plus is plus. So 2.3 into 2.3. 0.7 into 0.7, 0.3 into 0.3, 0.1 in 3 into 0.13, 0.17 into 0.17, 4.7 into 4.7, 3.7 into 3.7. You will get the individual figures like this. So the total is now 64.1. The total is 64.1. The total of all these. So the total of all this is 64.1. This is called as sum of squares total. This is called as SST. If you remember 64.1, where did you see? You saw here. You remember, this is 64.1. This is 64.1. Now you got the answer how to calculate SST, sum of squares T. And in the Anova table, you got 64.1, and I showed you how you got this 64.1. Next one. So our first part of our Anova table, which is sum of squares total, we have found out. We have found out sum of squares total. Sum of squares total. Now we will find out sum of squares error. So the formula for finding out, we will find out. So this is one part which is used for finding out SST. Now we will find out this part to find out sum of squares error. And sum of squares error is 12.3. We will find out how we have arrived at 12.13671562. Let's calculate it. So the formula, first column, second column, third column, fourth column, fifth column are discussed. Now let's discuss about the sixth column. The sixth column is y minus, this is y minus y predicted. Y predicted. So I have predicted this much, but I should have predicted this much, and there is a error, and this error is this much. Okay, so this error will speak about sum of squares error, or sum of squares residual. So I have found out the error. This is error. The first case, the error is 4 minus 3.76 is 3.2387. In the second case, 5 minus 4.5 is 4.49. In the third case, 6 minus 5.25 is 7.748. In the fourth case, 5 minus the error, which is 5 predicted is 5.9. You will get, in case in the third, sorry, I will repeat once again. 4 minus 3.76, we will get this. Just a moment. 4 minus predicted will give you this one. 5 minus predicted will give you this one. 6 minus predicted will give you this one. 5 minus predicted will give you this one, and similar lines. Now, after you found out this column, just square them to find out sum of squares of error. So y minus y predicted square. So 0.238 square, 0.49 square, 0.748 square, 0.99 square, 0.88 square, 0.85 square, 2.23 square, 0.34 square, 1.9 square, and so on and so forth. So These are the squares of this column, that is the error column. So sum it, that is called as sum of squares error or sum of squares residual, and you will get the figure as 12.13. Now you might have seen this particular 12.1367 in case of Anova table. Let's see. Yes, 12.13, 12.13672 is, so we have calculated this and we have calculated this. Now let's talk about how to calculate sum of squares regression or sum of squares model. So this is also called as sum of squares. How do you find out this value is our now next part of our discussion, that is sum of square regression, which is also called as sum of squares model. Now let's put our whole concentration in finding out that particular uh, sum of squares model or sum of squares uh, regression. Now, so what is the formula? First, this is the two tables which you have to prepare in the given table. So y average. So this is the y average minus y predicted minus y predicted minus y predicted. So it is 7.3 minus 3.76 will give you this figure. 7.3 minus 4.5 will give you 2.79. 7.3 minus 5.25 will get 2.04. 7.3 minus 5.99 you will get this figure. 7.3 minus 7.11 you will get this figure. 7.3 minus 7.88 you will get this figure. 7.3 minus 8.23 you will get this. 7.3 minus 93.84 you will get this one. 7.3 minus 10.09 you will get this one, and finally 7.3 minus 10.83 you will get this one. So this is the way you find out the values of this particular column. Now square of, you just square the individual uh, observations. So 3.53 square, 2.79 square, 2.04 square, 1.3 square, 0.86 square, zero point 0.5 square, 0.93 square, 2.04 square, 2.79 square, and 3.53 square. And this is the square of y average minus y predicted. And you sum all these figures. Sum all these figures, you will get 51.963267. So just remember 51.963. Let's see whether I got it in the ANOVA table or not. So ANOVA table is showing yes, 51.963 precisely. So hope you understood the calculations of ANOVA table. Calculations of ANOVA table. A part of you, of this has been discussed. A part of this has been discussed. Now we will find out. Uh, we will find out. This I will discuss later. This later. But already we have found this. We have already found this. We have already found this. Now let's talk about this one. MS, or this one is MS, that is mean sum of squares of regression, mean sum of squares of regression, and mean sum of squares of error. So this was total sum of, this column was sum of squares regression, this column was sum of squares residual or sum of squares error. This column is mean sum of squares regression, and this column is mean sum of squares error. Now, how do you calculate? How we arrive at this particular figure of 51.9632 and 1.571, 1.1, 1.517089. So after you have calculated these figures, and I am going to show in the next discussion about this degree of freedom, how we got it. Now let's calculate how we got this particular figure. So what we did to find out this, this is nothing but this divided by this. That is sum of squares regression divided by degree of freedom of regression. So 51.96, 51.96 divided by 1 is equal to 51.96. Second one, how did I get 1.17089? That is a mean sum of squares error. This is nothing but SSE divided by degree of its freedom. So this is SSE, this is the degree of freedom, that is 12.13672 divided by 8, and you will get this particular figure. So hope you have understood this part of our discussion also. So next point is, how did we calculate F value? How did we calculate F value? F value is nothing but F is equal to, please remember this, divided by this, that is mean sum of squares regression by mean sum of squares error, that is equal to 51.9632 divided by 1.17089. So you will get 34.25196. So this is calculated, 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 this is calculated. So in the next forthcoming discussion, we will discuss how we got degree of freedom and how we got significance of S in case of a ANOVA table. Hope you have understood up to this stage. Okay, so the same calculations I have put here also. The way you have calculated these figures of 51.96, 1.57, 34. Just now we discussed about this one. So the same I have put in this particular PPT slide. Next one. Please remember, this is very important, and I will spend a lot of time on understanding this one. Okay. So this is I will just take 64.15, 51.96. Okay, just a moment. So here it is 50. The sum of squares total. The sum of squares total is 64.1. 64.1. The sum of squares regression is 51.96, and the sum of squares error is 12.13672. Okay, let's incorporate this in this particular equation. So this equation is very important equation. That is, this is SST is equal to SSM, that is, or SSR plus SSE. Already told just now in this particular session, before 5-10 minutes I have explained how to calculate SST, how to calculate SSM or SSR and SSE, that is sum of squares total is equal to sum of squares model or sum of squares regression and sum of squares error. Just now I explained. So let's put these values. So it is 64.1 as already calculated is equal to 51.96 plus 12.136, something like that. Okay, so 51.96 plus 12.13 is almost this value 64 point. If I increase to 0, it is 1. So this is the way we have to understand the equation. So y minus y bar, I told you, look at this y minus y bar. All these tables which are there are the derivations of this equation. Y minus y bar whole square is equal to y hat minus y bar whole square plus y minus y hat whole square. That was precisely what I did when I did all these calculations. Please remember this. Okay, if there is an element of doubt in this particular slide, you can keep on visiting, and one day you will become a master, because none of everybody on this earth will master only if you repeatedly look at that concept on a regular continual basis till the time you master it. So I have also learned by putting my heart and soul and my time on this regression. So that's the reason I am able to explain it. So once again, let's incorporate the results. This I got it as 64.1 is equal to 51.96 plus 12.14. So if I total this plus this, you will get 64.1. So y minus y bar whole square is equal to y hat minus y bar whole square plus y minus y hat whole square. So now what is this? This is the total variance. This is the explained variance, and this is the error or the left out part or the residual, which is called so called as unexplained part. Already I told about this. This is so I will just this is the unexplained. This is the total variance. This is the explained predicted variance. This is the predicted variance. Look at this. Okay, this is the actual variance I should have predicted. I should have predicted how much I have predicted this much, and how much was not predicted this much. In the second case, this was to be predicted. This was the variance. This was the predicted variance, and this was not explained or the error. So the same way here also when I total it by squaring it. Okay, so 64.1 has to be explained, but out of 64.1, 51.96 only it has explained, and the remaining 12.14 is not explained. 12.14 is not explained. So a model is to be told to be very good model when the explanation power of the model is very high. Means out of 64.1, what is this amount? If it's almost near to 64.1, it's 100 percentage. If it is like 32, means only 50 percentage, because out of 64 only 32 is explained, the remaining is still remained unexplained. So this part should be very high and this part should be very low. For example, 64 in this case, 52 is explained and 12 is unexplained. So it's almost, I will call it as a 5 divided by 6 is 83%. So it's a very good model. It's a very good model. So you remember R square. R square is I will show you where you got this R square. This R square is very important. This is R square. This is R square. So hope you have cleared. This is R square. This is R square. So how do you calculate R square? R square is sum of squares regression by sum of squares total. So or you just square it. This is one method and this is the second method. This is the second method. This is the second method. So sum of squares regression by sum of squares total. This is the variance explained out of the total variance. Hope you have understood this. So let's go back to our original slide. So I have to keep on navigating from one slide to another slide because of the given situation. Okay. So what I mean to say is this numerator should be more and the denominator in comparison with the so out of this total variance this should be very high. Okay, for example, out of 64 in a different other model this ssm or ssr is 55 and this is 9 means now this is again becoming a very strong model because it is explaining the variance to the extent of 87 percentage. Another model on the same data you have incorporated some more new independent variables and you got this as 59 and the remaining unexplained is only 5. So in this case, it is 92% if I'm accurate. So 92% of the variance is explained. The total variance of 64 and it is explaining 59. Another example is 64 and 63 is the sum of squares to regression and only one is sum of squares error means the total sum of squares of error is only one, almost 99 percentage. Another case is 64, it is 64 and this is 0 means 100% of the model is explaining the variance of the dependent variable by the independent variable. Another case is 64, this is 20 and this is 44 means only 30%. This is not a strong model because the variance, the explanation power should be more than that is the R square should be more than 50 percentage. Then only in social sciences or in management sciences we state that yes it's a very strong model. This is also known as coefficient of determination. This R square is also called as coefficient of determination. So So we have seen till so far this one, and this is a number of observation. We will find out in the further classes what does this mean and how it is calculated. How it is calculated. Now next one is calculation of multiple r. Very important calculation of multiple r. This 0.903664. How did we calculate it? How did we calculate it? Now to calculate this, let's take up this particular table, and I will tell you. You will be able to understand thoroughly all this. Okay, I have dedicated a separate video on calculating mean, median, mode, standard deviation, skewness, kurtosis, correlation, and I will put up this video uh, on YouTube on my channel. You can visit how to calculate this particular items, statistical methods. So now is see here we have found out this. We have found we have found out this. Now let's calculate how to find out this. How did we find out this? So multiple r is nothing but the given data y and y predicted. You just find out the correlation. You just find out the correlation. You just find out the correlation or apply correlation on this given data, and you will find out, you will calculate multiple r. You will calculate multiple r. Let's calculate. So I will have a separate video on correlation in the Excel, how to calculate correlation in Excel sheet. I will have a separate dedicated video on this data itself, on this particular data only. So this is y actual values. This is the number of hours. Sorry, these are the number of marks secured, and these are the predicted values of y. I told you and I showed you how you have calculated. So if you want, you can get back. So this is the predicted value of y. This is the predicted value of y. This is the predicted value of y. So this is the y value. So I have just taken these two columns in my PPT to find out multiple r. To find out multiple r. So 4 and the predicted is 3.765, 4.5, 6, 5.25, 5, 6, 8, 7.117, 7.856, 8.239, 9.35, 12, 10 and 11, 10.83. 10.83. Now, if you apply just correlation between y and y predicted, you will get 90 0 0.9, 0.9, 0.9. So please remember this is R value. Correlation is always symbol showed by the symbol R. So correlation in this case is 0.9, 0.9 means it's a very strong model. So please remember correlation values always lie between -1, 0 and 1. Correlation is always the values of R lies between -1, 0 and 1. Now what do you mean by 0? 0 means there is no correlation between the given set of data. What do you mean by 1? It's having a strong positive correlation. The set of data uh, is having a strong correlation. -1 means yes, there is strong negative correlation. One increases, the other decreases. In this case, one increases, the other also increases with the same magnitude. So if uh, so here, please remember the thumb rule. The thumb rule is the value of r always lies between the value of r. The value of r always lies between -1, 0 and 1, or that is -1 and 1. So if it's tending towards -1, it's a negative relation. It's tending towards 1, it's a positive relationship. So this is negative relationship, this is positive relationship. Okay, now if it's for example, if the results are in between like plus or minus 0 to 0.2, or plus or minus, the results are of r are plus or minus 0.2 to 0.4, plus or minus 0.4, or plus or minus 0.4 to zero point 0.6, or plus or minus 0.6 to plus or minus zero point 0.8 in between. That is what I mean. 1, 2, 3, 4. And last one is zero point 0.8 plus or minus zero point 0.8 to 0.099 or 1. So this is a very strong model. This is a, this is a very strong model. This is a strong model. This is a medium model. This is a weak model. This is a very weak correlation. Sorry, weak correlation. This is a very strong correlation. This is very strong correlation. This is strong correlation. This is moderate correlation. This is um, weak correlation. This is a very weak correlation because the output is only 0.2. In this case, please remember, in this case, when we run a regression and you get a table of multiple r square and adjusted r square, standard error, and so on and so forth. Please remember to look at this item, these two items, and I told you how to calculate multiple r. So multiple r is the relationship between the given dependent variable with its predicted variables, with the predicted variables. It's more than 0.7, because if it's more than 0.7, that is the correlation between y and y predicted is more than 7. It's a very strong model because 0.7 into 0.7 will give you r square. That is the strength of the model, which is 0.49. So this is a weak model. So it should be more than 0.7, like for example 0.75. This should be more than 0.75. Hope you have understood it. So already we have already spoke about coefficient of determination. Okay, so how 0.90 is this particular figure. Now square that one. You will square this one and you will get 0.18066, which is the strength of the model, or r square. This is 81%. So unexplained variance. Now, what is the unexplained variance? Now, if you look carefully here, you can have a correlation within y and predicted y, and the difference of y with predicted y is nothing but this one, error. So if there is a correlation like this, and if the now this should be high or low, as I already told, this should be very low. This should be almost zero. This should be almost zero, because the predicted value should be near to y, and when it is near to y, this is almost zero, means the error is almost zero, but it may or may not be, it may or it may not be. The unexplained variance. So now you just calculate, we have just now calculated the unexplained variance, the error of individual items. I got 0.23, 0.49, 0.77. If you remember this one, 0.23, 0.49, 0.74, so on and so forth. So the same figures I have taken here. Okay, now find out the correlation. So the correlation should be, for example, 4, if it is 4, for example, if this figures in place of this one, it is 3.5 or something like that, it's almost near. So means the unexplained variance is very high. So it should be uncomparable. It should be uncomparable. It should be away from the natural y. It's almost like 0 or 0.1, something like that. So when I find out the correlation, I will get 4.33. Then I will square it. I will get 0.189. So how did I get 0.189? Another way is you just minus 1 minus 0.1, 0.81, you will get 0.19. You will get the same figure. You remember, you get it 0.19. So the same, I have put total variance. The total variance is equal to, so this I have carried this 0.1, 0.81 I have carried. I have carried 0.189 I have carried in the next slide. So 0.81 and 0.1893, 0.1893. So this is R square, this is unexplained variance, this is the total variance. So this should be low, this should be low, this should be high. This should be high out of this. Out of 100 percentage, this should be high and this should be low. Like for example, 90%. So obviously this will be 10%. This is 70%. So this will be 30%. This will be 85%. So this will be 15%. This will be 95%. So this will be 5%. So this should be low and this should be very high, because the explanatory power of the model should be very, very high. The explanatory model of the model of the given equation should be very, very high. Next one. So this is carried again. So the same one, sum of squares explained by the regression, that is explained variance. Sum of squares of errors, which is unexplained variance, is 19 percentage. The total of sum of squares is 100. So r square is equal to sum of squares r by sum of squares t. So hope you remember this sum of squares of model, sum of squares of r by sum of squares of total. So this should be high out of this. So for example, this is 100, it should be 80. Now how do I get this one? There is another, just SST minus SSE. For example, SST is equal to 100, SSE is equal to, that is sum of squares errors or residual is 20, and sum of squares regression or model is equal to 80. So the strength of the model is, out of 100, 80 is explained. So here 80 divided by 100. Or another method is 100 minus 20 by 100 is again 80 by 100. So sum of squares total is equal to sum of squares regression or sum of squares model plus sum of squares error. So as already told and explained and hammered you by continuously emphasizing on this, and on this, I told this should be very high and this should be very low. Then only the model is to be told to be a very strong model. Very strong model. So all I have shown already, this has been explained to you in the previous slides. If you remember, this was the, if you remember, this is the same which is incorporated here in this slide. So you got 64.1, you got 12.14, and you got 52. Now the same I have used. Sum of squares total is equal to 64.1. Sum of squares residual is equal to 12. Sorry, sum of squares regression or model is equal to 12.1367, and sum of squares error. Sorry, this is error. This is error. Just a moment. This is error. This is error. Sum of squares error or sum of squares residual, and this is sum of squares model or sum of squares regression. So sum of squares total is equal to sum of squares residual. You can just write this over this, and this you can write it here. So r square is equal to sum of squares error residual, that is sorry, sum of squares model. This is 51.96 by 64.1. Another way is sum of squares total 64.1 minus error is 12.13 by total 64.1. Same, one and the same. So the same I have carry forward, and when I calculated by dividing 51 point, that is the explained variance with the total variance. This is the total variance. This is the explained variance. When I divided the explained variance by the total variance, I will get 81.5, which is called as the strength of the model. 81% is explained. The best linear model minimizes the sum of squares error. Okay. So this again is very, very important. Uh, so these are all case 1, case 2, case 3, 4, 5, 6, 7, 8, 9, 10. These cases I have told, I've just put it on PPT to make you aware about the understanding of strength of the model, strength of strength of the model. So for example, case 1, case 2, case 3, case 4, case 5, 6, 7, 8, 9, and 10. So here the total Sum of squares is 100 in all the cases. Now, what is happening to SSR? That is sum of squares model. How much is explained? This is explained. So this is unexplained. This column is unexplained. So 100 is explained, 90 is explained, 80 is explained in those in respective cases. So on and so forth. Now sum of squares error. Sum of squares error. So sum of squares error is nothing but SST minus SSR. That is 100 minus 0, 100 minus 90, 100 minus 80, 100 minus 70, 100 minus 30, 60 is equal to this much, 100 minus 50 is equal to this much, 100 minus 40 is equal to this much, 100 minus 30 is this much, 100 minus 20 is this much, and 100 minus 10 is this much. Now let's discuss about the strength of the model. Here 100 divided by 100 means the total variance is 100, and the total explained also is 100. In the second case, out of 100, 90 is explained. In the third case, out of 100, 80 is explained. Out of fourth case, 100, 70 is explained. Out of 100, 60 is explained. Out of 100, 50 is explained. Out of 100, 40 is explained. Out of 100, 30 is explained. 30% is explained. Out of 100, 20 is explained. Out of 100, 10 is explained. So this is the explained. So opposite of unexplained is unexplained. So unexplained is 0, unexplained is 10 percentage, 20 percentage, 30 percentage, 40 percentage, 50 percentage, 60 percentage, 70 percentage, 80 percentage, and 90 percentage. So up to this is okay. Up to this is okay, because the unexplained is when it is more than 50 percentage, then the model is a very weak model. So this is not explained because the unexplained is 60 percentage, the unexplained is 70 percentage, the unexplained is 80 percentage, the unexplained is 90 percentage. So your unexplained or explained percentage should be more than 50%. Then only the model is told to be a very strong model. Hope you have understood up to this stage, and in the next class we are going to talk about some more results which are there when you conduct a regression model in Excel or SPSS or any statistical tool, and I am going to explain the degrees of freedom, standard error, and other aspects. So we'll stop here and we'll join in the next class. Thank you so much for your patience listening.